for this, if you did draw two circles, you do need to make sure that the overlapping part was also included. Because if it says probability of A, it still counts A even though it overlaps with B. Probability of event not A, if that circle's A, it's everything on the outside of the circle. Again, if you had two circles there, that's fine. Make sure you have everything outside the circle of A filled in. Probability of both A and B, I kind of told you about that. Both A and B, that's both, that's frown, that's an intersection, so you should just have that. Union A or B, I kind of give you an example of that one already. That's everything in A, everything in B, or everything in both A and B. Probability of only A. Look at what it's telling you. It's A and not B. It has to be A and not B. And again, for all of my pictures, A is on the left, B is on the right. A and not B is just that filled in. The intersection is not filled in on that one. It can't have any part of B in it, so it's not filled in. Probability of only B. Probability of not A and B. So there's A, there's B, and again, it'll be just that. Yo. A's always, this is A, this is A, B is on my right, A, and B, and then A, and B, and B. Question?
For number 2, if there was a B, would you shade it in?
Yeah, for number 2, if there was a B, which you guys could have had, it would be like this. We want the probability of not A. If that is A, not A is everything on the outside, which most everybody gets. And then also that part, because that doesn't have any A in it.
And what about number 4? Should it be shaded around it?
A or B, it can't be shaded around, because on the outside it's not A and not B. And this is everything that's A, everything that's B, or everything that's A and B, which is the left, the middle, and the right. That make sense? Okay. I don't know if it's going to carry my ink. Probability of exactly 1. Exactly 1. This is saying everything that's A and not B, everything that's B and not A. So hopefully you have something filled out like that. The intersection you can't count. Okay? Everything that's A and not B. Everything that's A and not B. If my left is A and my right is B, everything that is not that is A but not B is what I have shaded right there. Everything that is B but not A is shaded over there. This might help. I'll shade that in red. A union means this or where they touch. In this case, they don't touch. They don't overlap. So that's just the answer. Probability of not A and not B. Not A with not B. It's got no A and no B in it. That's all the outside. It's this part here. Okay. Any questions about those shadings? Are we okay? How about a fist of 5? Have we done fist of 5 in this class? Fist of 5 on how we are with these Venn diagram stuff. Okay, cool. All right, vocab word. Right here. Disjoint or mutually exclusive events. Disjoint or mutually exclusive. I probably want to write it down. Some of you guys may have had the picture correctly. Disjoint or mutually exclusive. They don't touch. Okay. Disjoint or mutually exclusive events are two events that don't touch. There's no intersection. For example, it might be something like people who have blue eyes and people who have brown eyes. Do we agree that there's no intersection? People who have both blue eyes and brown eyes. For all intents and purposes, we're not counting contact lenses or anything like that. Okay, any questions about disjoint or mutually exclusive?
Bless you. You'll let them know.
All right. Now we're getting into stat stuff. Okay. We're going to assume that Tyreek shoots 80% from the free throw line. DeMarcus Cousins shoots 70% from the free throw line. The probability at two different times, obviously, that they both make the free throw is 65%. You're going to use this information and answer these questions. Here's what I would do for this. Draw a picture, not a picture of them shooting free throws. Make a Venn diagram picture. Because I think we have a kind of an understanding of probability. It just means, this means on average, if Tyreek were to shoot 100 free throws, he'd make 80 of them. Do you agree 80%? That's what that means. 70%, if he shoots 100 free throws, he's going to make about 70 of them. All right. So for this problem, I'm going to make a Venn diagram. See if I can set my sheet. I have it. Where's mine? There's a special pen I have. I don't know if this is it or not. That didn't do what I wanted it to do. It's cool, but it's not what I wanted it to do. Anyway. Venn diagram, circle, circle. And what are we going to say? We're going to say A. We're going to go Tyreek. We're going to say A is Tyreek making a free throw, and B is going to be DeMarcus make a free throw. Okay. So I'm just going to even write Tyreek and DeMarcus. Okay. All right. Let's start with what we know. Do we agree? My red circle here, the whole red circle, is the probability that Tyreek makes his free throw, which we know is what? 80%. Okay. The whole red circle is 80%. Great. Here's what we need to work with, though. We know that the probability that they both make a free throw, the probability that they both do it is 65%. So really, the probability that they both do it, which is right in here, is what? 65%. I'm going to write my percent because we're going to start working mathematically with our calculator and stuff like that. So is it okay if I write 0.65 for 65%? Okay. So 0.65 is going to go right in there. We agreed that that's the probability that they both make a free throw. So that's 0.65. A lot of this work today is going to be kind of critical thinking. If the whole red circle is 80%, 0.8, and what's overlapping is 0.65, then what's left over here? Shouldn't it be 0.8 minus 0.65?
Yeah.
Okay.
0.15.
0.15? So that number is going to be 0.15. So are we okay with that, General? That's kind of the hardest thing we're doing today. All right, let's go over to DeMarcus. Same game. Everything for him is going to be in blue over here. He makes it 70% of the time. Which, if they both make it 65, he's only making it 0.05, and I get that from 0.7 minus 0.65. Okay. Next kind of question. We've got that. This kind of situation, what do all the probabilities need to add up to be? 100%? How many people agree with that statement? Okay. If all the probabilities need to add up to be 100%, how can I figure out what's on the outside? What's left? Good. Add it all up and subtract from, in this case, 1, right? Because 1, does we agree the probability of 1 is 100%? So I'm going to go 1 minus 0.15 minus 0.65 minus 0.05. And that's going to leave me what's on the outside. I don't know what that is. A 5. 0.05? 0.15? 0.1. So now that we have all the probabilities represented, basically taking some language and making it a picture that we comprehend. Any questions or clarifications getting that diagram? All right. So the question is, find the probability that at least one free throw is made. At least one free throw is made. Is it okay if you make both? In other words, is it okay if Tyreek and DeMarcus make it? Okay. Is it okay if just Tyreek makes it? Is it okay if just DeMarcus makes it? Okay. So if we want to look it out in kind of critical thinking, it should make sense. If we're looking for at least one free throw, it should make sense that it's going to be 0.15 plus 0.65 plus 0.05. That would be Tyreek only, them both making it, or DeMarcus only. So the probability that at least one free throw is made, this is part A, is going to be 0.85. That should make sense for us. By the way, that is the union. Right? The union. It's or. Tyreek makes it, or DeMarcus makes it, or they both make it. Notice what we just talked about with the Venn diagram is now matching up with what we have in this probability table. Okay. Probability, part B, that neither free throw is made. We already have that on our chart. We just need to figure out where it's at. Yeah, it's 0.15. This is where they both miss. 0.15. We could write this in terms of a probability, just to get you guys familiar with the language. Do we agree that's the probability that Tyreek not, that's complement, Tyreek not, Tyreek C, do we agree? Intersecting and DeMarcus not. Do we agree with that's what that is? In terms of stat language. I'm just trying to compare stat language to what is being said here. 0.15 for that. Probability exactly one free throw is made. Well, where is exactly one free throw made? That is this part over here, Tyreek only making it, or this part over here, which is DeMarcus only making it, which is going to be 0.2. Agree with that? So far, I see us. Are we, again, 55 for easiness right now. Is this pretty easy? I look at us kind of like we're half asleep, so is this super easy? Okay, just making sure. All right. Any questions on that problem or what we're doing, how we're doing it? Next one. Consider the event a coin is flipped twice. So I can take a coin, I'll flip it. Oh, what's that? D. Oh, D. Find the probability that DeMarcus makes his and Tyreek misses. What is that? DeMarcus makes his and Tyreek misses it. Where is it? Should be 0.05. It's written right there for us. Again, it's right here in blue. Probability that DeMarcus makes his and Tyreek misses. Right over here, 0.05. DeMarcus makes it, Tyreek doesn't. I forgot part B, sorry about that. All right, next thing. Consider the event a coin is flipped twice. Another vocabulary word right here, sample space. Sample space just means all the possible outcomes. In this case, there's 4. So sample space means what can happen. What are we doing? We're flipping a coin. Do we agree? In fact, how many times are we flipping a coin here? 4? Twice. So, if I'm flipping a coin twice, on the first toss, what can happen? I can get a heads, or I can get a what? Okay, that's my first toss. So if I look at it in terms of x, comma, y, then x is going to be first toss, and y is going to be second toss. My sample space is going to be all the things that can happen. So one of these things can happen is I can get a head on the first coin, and I can get a what on the second coin? A tail. Okay. Another thing that can happen is I get a tail on the first coin and a what on the second coin? A head. What else can happen? I can get 2 tails. Oops, put a comma there. Awesome. And the other thing that can happen is I can get a head. Any other possibilities that can happen here? Can it land on its side? We're going to assume that it does not land on its side. Has anybody ever seen a coin land on its side? Ever? What? I didn't say if. I said, has anybody ever seen it happen? You have seen it happen? I'm impressed. All right. Let's make it happen. Well, we absolutely can manipulate it. We just need to call Mythbusters guy, right? All right. Assuming a rare event, which would be the coin landing on its side, which we would agree is pretty rare, do we agree that these are the possible outcomes? Heads and tails, tails and heads, 2 tails or 2 heads. So again, sample space is all the outcomes. There's 1, 2, 3, 4 possible outcomes. There are 4 events in our sample space. Again, we're looking at probability. We don't need to make a Venn diagram here, but we want to calculate this probability. Find the probability that at least 1 tail is tossed. Yep, well, at least 1. If 2 tails are tossed, does that count as at least 1? So really, we want to look at, and I'm going to keep coming back to probability. Probability is really, I'll call success over total. And success can be defined many different ways. In this case, success is being defined as at least 1 tail. Okay? So we need to go look. And if we want to go back to the bucket, there's really 4 things. There's 4 events. There's 4 outcomes in the bucket. It is head, tails, tails, heads, tails, tails, and head, head. Find probability at least 1 tail is tossed. Does this count as success? Yes. Does this count as success?
Yes.
Does this count as success?
Yes.
Does this one? No. How many successes do we have here?
3.
Out of how many total? Who can answer the question? Yes, why? Why is there 3 successes here? Who can explain? Okay. So we're defining success as a tail. Heads, heads doesn't have a tail in it. Part C, you can hopefully start to see the method in my madness and instruction today. The probability that no tails are tossed. Do we agree that that's going to be 1 out of 4? Do we also agree that this is going to be a complementary event? A tail is tossed, at least 1 tail is tossed, or no tails are tossed. Notice that if you look at this probability, it's 1/4 plus 3/4. So you take the event plus its complement, and you will always get 100% of your data. Does that idea make sense? The complementary events will always add together to be 100%. You guys are going, if this chapter is just like this, why don't we start here, Mr. Wood? How are people saying that right now? Because it's not just like that, I don't know. Probability is usually one of the hardest parts. Supposed to be. I don't know. Might not be for you guys. 2 cars arrive at a stoplight. Probably the first stop is 60%, probably the second stop is 70%. Probability of low stop is 40%. You guys do this one. Make a Venn diagram and do it. What? Yeah. Yeah, stop sign. Stop light. Yeah. We're not judging it on its. Next thing we're looking at, probability. Some vocab words here. We will come back. You will have more time tomorrow because I'm going to have to catch the other group up that's gone today. So don't worry too much. Definitely on completing that worksheet, don't worry too much about that Venn diagram part. Do go ahead and make sure you can do number 4 and number 5 on there. You guys do have the ability to do number 4 and 5, so you should be able to finish those up. Want to look now more at probability. In fact, chapter 6 is really titled probability, so that's where we're going to be going. That is what we're about here. I'm just going to show you a quick peek at a picture. Here, this is a graphical representation over time of somebody doing an experiment. Okay? Their experiment is they want to calculate the probability, or basically they want to see what happens if they roll a dice 2,000 times. They want to know what the probability is of rolling a 1. And you guys know right now, if I sat here and rolled the dice and threw it against the wall, what's the probability that that roll would be a 1? 1 over 6. There's 6 outcomes there, 6 things in my sample space, and there's 1 success, which is the number 1, correct? Okay. What you see here is a graph of the relative frequencies as they roll the dice. In other words, they start at 0, roll 2,000 times. Now what happened was, at the very beginning, it doesn't mean if I sit there and roll the dice 6 times, I'm guaranteed 1 out of 6, correct? Everybody agree with that? I might get 1 out of 6, I might not. But if I rolled maybe that dice 20 times, what do you think? Actually, I'll make it this way. If I rolled the dice 18 times, do you feel a little bit better that I'm going to get 2, 3, or 4 6s? Does that make sense? Because 3 out of 18 is exactly 1/6, correct? So if I rolled it 18 times, I have good chances to get a 2, a 3, or 4 of a 1. Okay? So again, we'll kind of come back to this. I'm not going to focus too much on it. But what I want you to see, the only thing I want you to see is that as we increase the number of rolls we have, again, this is a picture of somebody rolling it 2,000 times. I want you to see that their frequency gets really close to 1/6, the percentage 1/6. In fact, as we get over here, it's just right on the line. What's happening here? We happen to get a lot of 1s in a row. What happens over here? We happen to not roll a lot of 1s. Does that make sense? Okay. So this is just kind of comparison of what theoretical probability is, and that's written in your notes there. Theoretical probability. That's what we assume to be true when we judge it in terms of successes over failures. Okay? The theoretical probability of rolling a 1 is 1/6. Then I can run an experiment and I can actually calculate the relative frequencies. You guys do know how to calculate the relative frequencies right now. Again, relative frequency is the actual trials, it's successes over totals. And then classical probability is what happens when we do it over time. We don't have time for the trial today, we might do it tomorrow. Law of large numbers is this. As you increase the number of times you do it, and again, that graphic that I just showed you, rolling a dice 2,000 times, the chance that the relative frequency, that's this thing here, this little red little line. Careful, Grace. This red little wiggly line. As I increase the numbers of frequency, my law of large numbers says that this will approach the theoretical. Okay? So my relative frequency will approach the theoretical probability. Okay? Again, relative frequency gets close to the theoretical probability. Again, this is one of the areas that calculus and stats blends together. It has to do with the idea of a limit, approaching it but never touching it. So, okay. So your three, it is vocab words at the top there: classical, relative, theoretical, and law of large numbers. Just have those down. All right. Suppose there are 3 girls and 2 boys in a group. Stats professor me randomly selects 2 students. Okay? Here's the deal. Here's how we think about things. We put them back into the Gatorade bucket. We put a lot of things in the Gatorade bucket before. My sample space, do we agree, has 5 things in it? People agree with that. 5 things in the sample space. 3 girls. I think 3 girls. 2 boys? 3 girls, 2 boys. So I got 3 girls, 2 boys in that bucket. And now what's going to happen? What is the probability that both students are girls? So that means I reach into the bucket and I pull out a girl. And then I reach into the bucket and I pull out another girl. Question is, how do we find this? You guys actually have done these things before. You just didn't know it. We'll formalize it right now. Let's take it this way. On my first draw out of the bucket, what are the chances that I'm going to reach in and pull out a girl? How many people agree? 3 out of 5. Okay? This is exactly true. Good question. With replacement, without replacement? For this calculation, I'm going to do it without replacement. Okay? The directions will be, read your homework tonight. It'll say with replacement or without. Our second pick, and this one, I'm not throwing them back in. I want 2 unique girls. Does that make sense? Because I'm going to be forming a group of 2. Okay? So my first one, I've got 3 out of 5. I reach in, I get a girl. Not only do I have to get a girl the first time, what has to happen the second time? I got to get another girl. But here's the catch. How many girls are in my bucket now? How many girls are in my bucket?
2 girls in the bucket.
2 girls are in the bucket. How many people are in the bucket? 4. To find the probabilities, we multiply them together. Okay? To find the probabilities, we multiply them together. So, this gives us, we can simplify within 1, 2, 3/10. Got all your Dave to have your test stuff. Did you get there? Oh, you guys just came from back. No, you're coming back. You won. Thank you. All right. What is the probability that both students are boys? Same game. How many boys are in the bucket to start with? 2 out of. And then there's going to be what? 1 out of 4. Is this game easy? Should be. Does it make sense that the probability of pulling out 2 boys in the group is a smaller probability than pulling out 2 girls? That should make sense. Why? There's more girls in the bucket than there are guys. Okay? This one's harder. What is the probability that at least one of the students is a girl? What needs to happen for that one? At least one of the students is a girl. We have different situations here. Does that mean I can pull out a girl and then a boy? Will that work? So let's think about this in terms of sample space. Can I pull out a girl and then a boy? Does that work? At least one is a girl. Can I pull out 2 girls? Okay. Can I pull out a boy and then a girl? Is there any other ways I can do it? Well, that wouldn't satisfy this. There's another thing I could do. I could pull out 2 boys. That's correct. But now, do I know how to calculate this probability? A girl and then a boy. Do we know how to do that? A girl is 3 out of 5, and then a boy is, it will be 2 out of 4. You took a girl out. Okay? Does that make sense? A lot of thinking going on today. The calculations isn't too bad. A girl and a girl, we actually already have that. But to show you again, that's going to be 3/5 times 2/4. Wait a minute. That's the same number, isn't it? Okay, now thinking in terms of probability, this one actually represents the two boys, right? This one actually represents the two girls, but the numbers don't care whether you're a boy or girl. It's just a calculation we're doing. And then a boy and a girl. A boy and a girl is actually going to be, let's see, a boy is going to be 2 out of 5 times a girl, which is going to be 3 out of 4. What do you notice about all those? They're all the same, right? All right. What was that? 3/10? So are you guys okay? I'm going to go 3/10, 3/10, and 3/10. And what am I going to do to those probabilities? Am I going to multiply them together? No, and this is one of the areas that's hard about probabilities of students. I got these numbers, but now I want this to happen, or this to happen, or this to happen. When it's an or, what am I doing with those probabilities? What did you do earlier? Didn't you add them up? Okay. So it's 3/10 plus 3/10 plus 3/10, which is 9/10, which is 0.9. So the probability that you get at least a girl when you reach in and pull out 2 girls is 0.9. It's going to happen pretty frequently. All right. Thinking caps put on here. Thinking caps put on. Do we agree that in this sample set, the only other thing that could happen is a boy-boy? Okay. Do we agree that all of these probabilities must add together to equal 1? We talked about that earlier today. So instead of doing all this work over here in blue, couldn't I have done this? 1 minus boy, boy. And wouldn't that give me that answer? Because isn't that a complementary event? And didn't I have that calculation already done for me? So couldn't I have gone 1 minus 1/10 up here? It's a match. Multiple ways to get the same answer. I would have done it in terms of a complement. I don't care which way you do it on your test. I care that you're statistically sound in the way you do it. Any questions or clarifications on that? All right. Probability that the students aren't the same gender. How do we do that? This one plus that one. How many people agree with that? This one plus this one. Is it going to be 3/10 plus 3/10 or 0.6? What? What's the question? I didn't hear the question. Okay. Any questions on that for same gender? Is everybody? Different gender. All right. This one. Mutual fund company offers customers several different funds. Money market fund, 3 different bond funds, 2 stock funds, a balanced fund. Among customers who own shares in just one fund, the percentages break down as follows. This is just a breakdown of percentages. Answer the questions. I'll go to the next one. What's the probability a selected individual owns a share in the balanced fund? This is almost reading comprehension. A share owns a share in the balanced fund. Let's see, balanced fund, 0.07. Yes, ladies and gentlemen, that easy. Let's see. Individual owns a share in a bond fund. It'd add 3. I can have a short-term bond, intermediate-term bond, and a long-term bond. 0.3. Lastly, probability that is selected. I'm going to go blue. Probability a selected individual does not own a stock fund. Does not own a stock fund. Do we agree it's going to be 1 minus stocks? How many people agree? That's what you got to do. 1 minus 0.18 minus 0.25. The other ones, I'll write that work in here. That's going to be 0.15 plus 0.1 plus 0.05. The balance fund is 0.07. Does not own a stock. We know that 100% added together. Take away the stocks, then you've got not owning a stock. What is it? 557? All right, what do we got there? 0.3? Fine. No, 0.3. Questions? Or wish we would have started here? Wish we started here. All right. Good part of the day. I'm going to make you guys a deal. Here's the deal. You get to roll the dice. You're going to pay me for the opportunity to roll dice. Okay? In fact, you're going to pay me $50 for the opportunity to roll this dice. But here's the deal. If you roll a 1, 2, or 3, I will give you $100. Okay? If you roll a 4 or 5, I'm going to give you $25. And if you roll a 6, you pay me $50. My question to you, do you want to play my game or not?
No.
No, because I'm a bad teacher and I rigged the game somehow? Do you want to play the game or not? Now, what we're going to do to calculate this out, this is actually called expected value, and this is something that is on your formula sheet, so we will be doing it. I framed it in terms of this question, in terms of let's make a deal. But you will have to do expected values. You decided you want to take a deal or not?
Oh, no, I wouldn't do that because, that's, it's people, whatever floats your boat, but gambling is illegal, so.
This is all theoretical probability. I'm not saying I'm actually playing this
I'm
game.
sure you knew that I have to report you to the authorities.
I'm just saying, maybe I should rephrase. Theoretically, if I was going to offer you this deal to play this game, would you take the deal or not? So, I just got people saying no, but of course I'm going to ask you yes or no. I want to know why you're going to say no or why you're going to say yes. What? You think I'm this evil guy who's only going to play games where I can take your money? You're probably right. Yeah?
Because if you play it, you only have a 50% chance of gaining money back. Well, you have a 50% chance of losing money, or I don't know.
Let's figure out a way to put this thought together. How many people understand the dilemma? I've got a chance to win some money, but I also have a chance to lose some money. In fact, right here, you're paying me $50. Right here, what's actually happening? You're still losing $25, right? You paid me $50. You're only going to get $25 back. All right. How are we going to do it mathematically? How are we going to do mathematically? Let's try to figure it out. Let's look at some probabilities. Let's look at what's happening. And some of you guys already said it. I heard somebody say, well, 50% of the time you're going to get how much money? How do we get 50% of the time anyway? 1, 2, and 3? Okay. So in terms of probability, if I roll a 1, 2, or 3, I win $100. So I'm going to write that down as 3 times out of 6. Again, isn't that success over total? Okay, 3 times over 6. I'm going to win $100. Okay? So if I want to kind of put this together in terms of probability, half the time I'm going to get $100, and that's what some of you guys said, right? Okay. Also, what's happening? 2 times out of 6, I'm going to give you what? $25? You guys agree with that? Okay? So this is really the game part right here, right? We're trying to figure out the game part. And then 1/6 out of the time, you're going to lose, what is it, $50? Yeah. Okay. Okay. This is a negative 50. No, this is just the game. Okay, this is just game. So let's look at it this way. Just playing the game, if I offered you to play the game for free, would you want that game? Or if I offered to play the game, but you had to pay me $25 to start with instead of $50, would you want to play the game? If you had to pay me $100, we're going to look at that in just a sec. So I'm only looking at just the game here. So for my 3 times out of 6, what's that? That reduces to 1/2, doesn't it? And then 100 divided by 2. That kind of comes to $50 in terms of a calculation. So we call that expected return. 50% of the time of 100, I'm going to get $50. This one goes in, 3 doesn't go into 25, even we're going to leave that at 25 over 3. And let's see, this one doesn't go in evenly. We're going to make that negative 50 over 6. Can I reduce negative 50 over 6? What is that? Negative 25 over 3. Do we agree with that? So, if I add this up, boom, boom, and boom, 50 plus 25 thirds minus 25 thirds, do we agree that's going to be $50? Do we all agree with that? So, I will tell you this. Your expected value, if I offered to let you play the game for free, you should definitely take that deal. Because on average, you're expected to get $50. Does that mean you're going to get $50 every time? No. In fact, I don't think in this problem you can even get $50 every time. You either get 100 or you get 25 or you lose 50. So you roll the dice. For you as an individual, however, you're thinking, I've got an 80%, better than 80% chance. What's 1 out of 6? Anybody know? That's 1 out of 6. I don't remember what that is. 18%, something like that. That's not. All right. So if I didn't charge you to play the game, your expected value is $50. Is everybody okay with how I got that? You take the probability times whatever it is. Probability times whatever it is. That's your expected value. Okay. Now, I said I'm going to charge you $50 to play this game. So your investment is $50, and you're expected to win. I'm going to put minus 50 for your investment. You're expected to win $50, which as an individual, you don't win and you don't lose. Does that mean each person in class when they play this game is not going to win or lose? Absolutely not. If I gave this to you guys as a classroom and we did it over and over every day, I would tell you at the end of the term, I would lose $0 or close to 0. I might pay a little bit, I might lose a little bit, but I wouldn't really lose that much. Some of you guys might lose a lot of money. Some of you guys might win a lot of money, but the amount of money out of my pocket is going to end up being close to 0. Why? Because I'm charging you and I'm giving out almost the same amount. In fact, in this problem, it's the same amount. Do you see how that expected value works? Any questions on that expected value? All right. Last problem for the day then. I want you guys to do this. Prison official knows that half of the inmates stay only 1 day, a quarter of the inmates stay 2 days, a fifth stay 3 days, 1/20th stay 4 days before they either release or they get sent to county jail. What I want to know is how long they stay in prison based on those facts. In other words, find the expected value.